Okay, maybe I introduce first our industrial affiliation program. It's a platform of our collaboration working together with industry. It's based on the cost sharing, but also IP sharing. So partners inscribe to our platform, to our industrial affiliation program. We run 3 technological platforms. One which is more nearby industry is based on, we call it IPERC platform, which develop PERC and N-type and P-type PERC technology. Second one is IBC platform, and then maybe another one, third one is long term, we call it epifoils and I modules. Epifoils and modules in very thin 40 microns foils and related to this cell technology. Within these 3 platforms, we are at this moment progressing strongly in the last year. In the IPERC platform, we have announcement of very good development in the nickel copper plating technology, when is a technology which we believe could replace in the very near future expensive silver screen printing. It gives us not only efficiency improvement, but it also drive costs down. We shouldn't talk only about the cost of the copper, but the combination of nickel silicide and copper enables you not only to save on the cost on expensive silver, it enables you to generate a new type of the cell structure. It helps you to increase cell efficiency. Silver is expensive, but has also certain limits which impose on the cell efficiency. It's not easy to have very good contact. It improves continuously, but still always implies when you have to go work with emitter with a highly surface concentration, and this limits you how efficient your emitter could be. When you replace silver with nickel, when your contact resistance goes drastically down, you can improve your emitter, you redesign your emitter, your efficiency immediately increases. And when you grow on the top of a nickel, you grow your copper, which is 100 times less expensive as a rare material, as a raw material than silver, so it gives you also efficiency increase and gives you also cost down. We have IPEX platform, as we call it, work on the P-type and N-type. And our work is shifting now more to the N-type. N-type because we believe it has higher efficiency threshold. P-type is now in the industry, industry is working very strong, is implemented. We have a presentation yesterday with very good results from industry. But we know that P-type wafers, we have certain efficiency limit and we have a light-induced degradation. N-type, the way how N-type material has much better quality. Yeah. We'll have less problem, we believe, with the implementation with the copper stability, with copper on the front side. We work with N-type with rear junction, so junction is displaced from the place when we deposit copper. So we think it will be reliability will be less of problem in this case, and efficiency limits are higher. So it will allow us to introduce, I think, copper faster into industry and get efficiency limit well above 21%. There are no principal reason why N-type should be more expensive than P-type. The only reason can come from technology. We know that in N-type, the range of resistivity which you get in one ingot is much wider than in the P-type. So it means you need to have a technology which accepts cell process and cell technology accepts wide range of resistivity. Once you have this, there is no reason why it should be more expensive than P-type. The only reason could be the scale of the production. P-type is a mainstream technology, it's a wide scale, there is a strong competition. This economy of scale plays a very important role there. For N-type, this should come. And we as a research institute, we should prepare something what will come in the industry. That's why we are moving on to N-type. There is no technological reason why N-type should be more expensive. We are working on cell structure which should accept wide range of resistivity, so we can utilize all ingots. And then we are sure will provide higher efficiency than P-type at this moment is able to do it. And we can compare in doing with together with nickel copper plating, we should also put the cost down. There are several elements. One, uptake of the PERC really in a real production line. And we're talking about the PERC technology already for several years. It's concept is very old, more than 20 years, almost 25 years. Yeah? So it took a lot of time, but now is real production. People are producing above 20% and in production line, mass technology. It's silicon based, so we still, you see, it's silicon is still dominating, it's growing. This is on the industrial, on the production scale. If we look on the from other aspects, I think perovskite, which is new type of materials, new type of cell concept, which make enormous progress from the moment, for instance, report to the high efficiencies, which is very short time. Its progress is much shorter than other technologies. I hope that we get more information about this type of the cell in the near future, in coming months, in coming years, so we can estimate. There were a lot of new technology in the past, which were disappeared later, so it takes time to really evaluate. Carbon nanotubes, again, progress in 1 year. We had a 4%, maybe 3-4% 1 year ago, and now people are reporting around 14%. So this has to be compared with the silicon. Silicon is always trying to defend. What I was also surprised by one of the talks, that the silicon is cheaper now, seems to be in the production line than the thin films like cadmium telluride. This data which was coming here. So silicon is still standing there strongly on this field, and now a roadmap to how to go beyond 25%. People talking what we should do to get from silicon, when we have this brick wall or calculator on 25%, how we should go above 25%. So different cell concept. Stack cells, mechanical stack cells, wafer bonding is an opening session. So people looking to it, how to move to efficiency threshold in industrial solar cells higher and higher. We as an Imec, we are not working, I would say, on specific processing technologies. We are working on the cell concept, and we are looking which tools, which processing and technology will be most suited. One implant is one of the options. I think it's not that people who don't want to use it yet, there is nobody investing now. So there is no investment in any type of equipment at this moment, only what's going is upgrade. We see ion implant as one of maybe enabling technology to simplify back contact cell. So interdigitated back contact cell, when you have patterning problem, ion implant gives these solutions or promise to solve this by the masking and implantation. So can simplify process, which is like people can say 18, 21 steps to only maybe to 10 processing steps. So I think implant will come back. Will come back at the moment when people have to invest. At this moment is upgrade of existing line. But if you really want to progress, you have to look for new tools, and implant is one of them. Will it make a breakthrough? I can't tell it. Every year people coming with something simple, and if we talk about mass production, if we talk about silicon solar cells, which have to go commercially, simplicity is one of the elements. So if implanting will simplify the process, it will enter the industry. If not, it will stay out of the industry. So simplification, simplicity, simplification is one of the key words if we talk about the technology to enter or not to enter. In one of the exploratory research which we are doing now in Imec is nano imprint. It takes a lot of time. So we do exploratory, we do tests, we experimenting with nano imprint. We have to see how we can enter with this in our industrial affiliation program. The work which we are doing now, mostly in silicon base, is industrial affiliation program. We have partners, and partners also co-decide on which technology we should work. So we have it on the exploratory part, we do experimenting, we present to partners. At the moment when the interest will grow, we invest more in this. It's not yet in the mainstream of our development, but has a promise.